Hi guys, Audrey here, and today we're going to talk about a method called volume by slicing. And we're going to start by thinking about the volume of a sphere. If I ask you guys what's the volume of a sphere, hopefully many of you, most of you, all of you, will be able to tell me. Now, if you said that the volume of a sphere was 4/3 pi r cubed, you would have been correct. So our question today is, how can we derive that formula mathematically using integration? To answer that question, I am going to draw the Cartesian plane with the x-axis and the y-axis, and then I'm going to draw a circle on that Cartesian plane. Now we're going to take this circle and sort of flop it all the way around the x-axis back up to the y, back up to the where it started, and that's going to turn that into a sphere. So really you can just imagine that this circle that I have drawn is actually a sphere. Now, what I'm going to do is I'm going to go along the x-axis and I'm going to chop it up into little rectangles. Right now, I'm going to start at 0 just because we don't really need to draw all of the rectangles. I'm going to chop it up into little rectangles, similar to what you probably did in Cal 1 when you were developing the idea of an integral via Riemann sums. Now, I'm going to call one of the little rectangles, the base of it, delta x. So the base of a rectangle, we're saying is delta x. And that's just because that is what's changing. If we think about back in Riemann sums, that delta x, it's just the length of the base of the rectangle. It's b minus a over n. If we say that this left side is a and this right side is b and that there are n rectangles. So because we're chopping them up into equal lengths, we'll just call that delta x. It's our change in x. Now, kind of like I said, if I took that circle and flopped it around the x-axis and brought it back up to where it started, I'm going to do the same thing with one of these rectangles. So I've got this sort of rectangle like this. I'm pulling it out of the screen, down into the bottom part of my sphere, and then back up to where it started. What I'm ending up with, oh, oops, is something that looks like a circle, except that it's got some sort of width to it. So it's actually a solid that's in a circular shape. So we're going to call this a disk. Um, Now this disk right here, we know how to find the volume of it. So the volume of disk is just the area of the circle times that delta x. Now, let's go back and think about the equation of a circle. If we remember from high school, x squared plus y squared is equal to r squared is the equation of a circle. So that original circle I drew was of radius r. That means that's r, that's minus r, that's r, and that's also minus r. Now, if I think about this disk and what the volume of this disk is going to be, we have that delta x already. We just need the radius of this circle. Well, notice the radius of this circle, if I take a random x value, is equivalent to the height of that rectangle right there. And the height of that rectangle is just going from the x-axis all the way up to the curve. So the height of the rectangle, in other words, the radius of the circle, which I'm going to call big R, let big R be the radius of the circle, is just that distance between the x-axis and the curve. So all we need to do to figure this out is figure out what is the curve in terms of x. Well, right now we know that it's x squared plus y squared is equal to r squared. That means y squared is equal to r squared minus x squared, and y is equal to plus or minus the square root of r squared minus x squared. But we really only need to take the plus because we're thinking of this as distance. So the radius of my circle here is the square root of r squared minus x squared. We know the area of a circle is equal to pi r squared. So that's pi times the square root of r squared minus x squared. Therefore, the volume of my disk here is equal to pi times the square root of r squared minus x squared squared times delta x. So that's pi times r squared minus x squared times delta x. Now let's go back and think about what you did in terms of Riemann sums. You said, if I add all of those, the area of all those rectangles together, I get something that is approximating the area. Well, in the same way, if I add together the volume of all of these disks, that approximates the volume of the sphere. So in other words, the volume of the sphere is approximately equal to the sum I equals 1 to n of pi times r squared minus x squared delta x. And that x right there is really just the x value. It's actually x sub I. It's the x value at any point where we're looking at the height of that rectangle to get our radius. Now, take a second, think about it, go back to Cal 1. How can we get the actual volume of a sphere? Hopefully, you remember that we just need to evaluate the limit as n goes to infinity of that sum. So in other words, we're letting the width of those rectangles that we started with get smaller and smaller and smaller and smaller and smaller until it's practically negligible. So we get the limit as n goes to infinity, sum I equals 1 to n, pi times r squared minus x squared delta x. Now, if you don't remember this, it's not a big deal, but if you do, you might see that that is just the definition of the integral. So in other words, this limit right here is the Riemann sum definition of an integral. So that means my volume of the sphere can be gotten by taking this integral pi r squared minus x squared dx, where r is the radius of the circle that we use to make the sphere. Now we need to think, what are a and b? What are our bounds of integration? Well, if you look at this, when we start the rectangles, technically we're starting over there at negative r, and we're bringing them all the way up to r. But one thing I'd like to point out about this picture that I've drawn is that on the left side of the y-axis and the right side of the y-axis, the shape that we have is exactly the same. So in other words, it's symmetric about the y-axis, meaning that if I figure out what the volume is on the right side of the y-axis, the volume on the left side of the y-axis will be the same, which means that I can actually make this a little bit simpler to calculate by doing 2 times the integral from 0 to r of pi times r squared minus x squared dx. And this 2 right here is because we have symmetry about the y-axis. All right, well, we know how to integrate. That's a pretty simple integral to do, so let's go ahead. So this is 2 pi times r squared x, because in this case, r squared is just my radius squared. It's just a constant, minus 1/3 x cubed that I am evaluating between 0 and r. So this gives me 2 pi times r cubed minus 1/3 r cubed minus 2 pi times 0 minus 0. So this is 2 pi times r cubed minus 1/3 r cubed. That's 2/3 r cubed, which is 4/3 pi r cubed, which is exactly what we expected to get, what we thought we were going to get when we started with this, when we said, hey, guess what? We already know the volume of a sphere. So we were able to get it by using some sort of combination of Riemann sums and the Riemann sum definition of the integral and the volume of this disk that we know. All right, so take a minute to think about that. But then let's think about how we could extend this to other shapes. So what I did is I started with the sphere, I took that rectangle and I flopped it around. Well, it turns out I don't necessarily have to have rectangles. I can slice these things up really into whatever shape I need to create the shape I'm looking for. So if we were to generalize this more, our general volume formula would be that we're just looking at the integral from a to b of the area of whatever the shape is that we're going around. In this case, it was that circle, so we had pi r squared dx. And in the next video, we'll see how we could have different shapes to give us something like this. Yeah. All right, so I'll see you in the next video where we will hopefully come up with a more general way, step-by-step way of approaching this.